Hi everyone, my name is Indrajit Kar and I head the AI and Advanced Analytics division in Siemens Advanta India. Thank you for having us in GTC 2020 and we are delighted to share distributed aerial image segmentation and elevation classification using knowledge distillation. I understand this sounds mouthful, however, sit back and relax. You will have a very nice journey. With my colleagues and myself, my colleagues are Anindya, Sushri, and Vishal, who are going to go ahead and explain this solution very clearly, as well as they are going to introduce themselves in the consecutive slides. So this is the team behind this entire project. Starting from the left, it's Vishal Pandey, Anindya Chatterjee, Sushri Sulagnalat, Sudipta Mukhopadhyay, Indrajit Kar. So let's understand what do we have on a plate today. Okay, so first of all, GPU accelerated image pre-processing using OpenCV, which is Anindya is going to talk about it. Knowledge distillation, Shushri is going to talk about it. Model parallelism use cases, which I'm going to talk, and there are three of them. One on single machine distributed knowledge distillation for image classification, single machine knowledge distillation for altitude invariant object detection, and multi-machine distributed knowledge distillation for altitude invariant image segmentation. And finally, communication backends. Now, it's very important to understand the communication backends, which will be covered by Vishal, because we need to understand how these GPUs are communicating to each other. Okay, so that's a very interesting topic. Okay, and what do you need? What to understand this entire session would be prior knowledge of model parallelism. This model parallelism is not available out there on the web. So you would really need to understand model parallelism. And after a session, I'm sure you'll be able to understand a little better than what you currently know. Distributed RPC frameworks, distributed autograds, and multiple GPU training. Okay, so sit back and have a great journey with us. See, every AI ML project needs computational power. Specifically, if it's a video that we are using to model, or if it's a high resolution image that we are using, or it's a audio, or it's a high frequency time series data, it definitely needs GPU power. So let me just explain the distributed computing environment that we have. We call our distributed computing environment as AURA, which is Automatic Unified Recognition and Analytics. So we do not only perform computer vision, we also perform various analytics on these 8 GPUs. Note, we also have a TX2 system, which we are going to talk about in subsequent slides. However, we are using this TX2 device to go ahead and embed the models that we train on the GPUs. Why do we do that? Because let's say we are going to classify and extract temporal spatial information directly from the drone. That means the computation happens on the drone itself. Yes, you heard me right. Let's say segmentation. The segmentation happens on the drone itself, not when we get the data on an SD card and plug it back to our, let's say, on-prem machine. Not like that. The entire work happens on the GPU, which is on the drone. So that is where we are planning to go, and that is what we are researching on. However, let me talk a little bit on the infrastructure. The infrastructure consists of 8 GPUs, which are distributed among two servers or two systems, which has a Docker and a Kubernetes cluster. Also, it has a Python library, followed by we use IDEs like VSS Code and Jupyter. We use all the libraries from TensorFlow to PyTorch to OpenCVs, sklearns, StatMods. We also use HPCs like Rapids, Task, Wix, Numba, and Ray. So these are our scaling libraries that we usually use, followed by MLflow, Kafka, Airflow, and Kubeflows. So this is all we have in terms of infrastructure that we are leveraging in order to deliver deep learning to our customers and our partners.
Hello everyone. Good morning and good evening from whichever part of the globe you've logged in from. My name is Anindya and I lead the team for AI and advanced analytics at Siemens Advanta based out in Bangalore. We are excited to be part of GTC 2022 and looking forward to this event. So today I'm going to briefly talk about the implementations of OpenCV operations to run on a GPU. So the hardware or the setup that we have currently for this process or for this project is that we have a 4 Nvidia 3080 Ti for image processing and model training. Now, by default, the Python distributions for OpenCV CUDA modules are unavailable, and it needs to be manually compiled using GCC and CMake from the source code for the packages OpenCV and OpenCV contribute to get the complete modules activated and run on CUDA. The OpenCV CUDA module is a set of classes and functions that utilizes CUDA computational capabilities. It is implemented using Nvidia CUDA runtime API and is supported only on Nvidia GPUs. So to enable CUDA support, we need to configure OpenCV, as I said, using CMake with the with CUDA flag as on. So along with the with CUDA flag, to get a complete flow or the complete package running on CUDA, we need to enable the below or the mentioned flags, turn it on, right? We need to enable with CUDA, we need to enable build OpenCV DNNs, OpenCV DNN CUDA, enable fastmath, build OpenCV world, build OpenCV Python 3, CUDA fastmath, and CUDA arcpin. Now this also includes the compute capabilities for your GPU, right? So that you have to mention based on the version or based on the make and hardware that you're using. Now, when the flag is set and if CUDA is installed, the full feature OpenCV CUDA module is built and is ready for use in Python or the language that you're using it on. So if the module is built and CUDA is not available, then you would get a runtime exception, like a GPU not supported error code. So want to be careful about that. So here in this slide, we'll talk about a couple of operations that we have migrated to CUDA and it's currently running on the GPU. The operations are quite simple and are very common, commonly used in any AI pipelines. So let's take the example of CLIHI, a type of adaptive histogram equalization, which is generally used to improve the contrast in images. Right? It differs from ordinary histogram equalization in the respect that an adaptive method computes several histograms, each correspond to a distinct section of the image, and then it uses them to redistribute the lightness um, across the image. It is therefore suitable for improving the local contrast and enhancing the definition of edges in each region of the image. So the process of operation on a GPU is that first of all, we allocate a memory on the GPU and we upload the files there. Um, then we allocate a temporary output file on the GPU and then we process the image on the GPU and then we finally download the image from the GPU to the CPU memory. The other operations that we have done for this project are like thresholding, resizing, and then converting it into grayscale. So these are the operations These operations can be achieved using the functions that are being mentioned here. We use the cv2.cuda.threshold functions, cv2.cuda.resize, and cv2.cuda.cvtcolor functions for the above mentioned operations that we have used. So this is one of the operations that we definitely wanted to migrate to the GPU, as it was taking a huge amount of time on the CPU. Um, the fast NL means denoising algorithm was not available by default when the OpenCV CUDA modules were compiled. So the function is available on the CUDA implementation on C++, but not exported by default. So to make it available, we had to modify the CUDA.hpp header file for the C++ source. It is available at the path mentioned here, the modules slash photo slash include slash opencv2 slash photos slash CUDA.hpp. We changed the function definition and changed CV exports to CV exports W for fast NL means denoising and fast NL means denoising colored, based on the requirement that you have on whether grayscale or RGB images. And we made the changes so that these source or these functions are available to us to be used easily. Now, this changes must be done before we build the source code using CMake. Now, attached is a small snippet of the code that we can use for the operation. The function parameters are slightly different for the CUDA version than it is for the normal one. So please refer to the OpenCV documentations if you have any confusion in that manner. So image processing can be a very computation intensive tasks. So if the user needs real-time performance in processing high quality videos, there is a good chance that a single GPU might not suffice, right? Um, so so let me give an heads up. So cv2.cuda.get CUDA enabled device counts returns the number of installed CUDA enabled devices. Right. So in the current version, each of the OpenCV CUDA algorithms can use or run on a single GPU. So to utilize a multi GPU setup, we have to manually distribute the work between the GPUs. So CUDA.set device, cv2 CUDA.set device can switch between active devices for the various operations. Right? We can manually slice and split the workload and pass it to individual GPUs for a distributed GPU setup, and then finally merge it back, which can give us a boost up to 2x in performance, right? If we split it into two slices. One thing to consider while we are dealing with a multi GPU setup is that it's always better to migrate to a multi GPU setup when we are working with heavier or complex algorithms only. For primitive functions, data pass overhead might eliminate the advantage that we are getting on for a multi GPU setup. So we have to think about that as well when we keep that in mind when we are doing a multi GPU setup for distributed OpenCV operations. So now we'll talk about the advantages, the disadvantages, and the future scope when using OpenCV and running it on a GPU, right? So let's talk about the advantages first. So once you have built it, right, using CMake and CPP, so it can be used exactly like you used OpenCV CPU code, right? There is no change. There's a little bit of syntactical changes, but nothing apart from that. There's a significant boost in performance. Like we have seen up to 30, 40, 50x speed improvements on certain operations, but it may vary based on the type of CPU and the type of GPU that you're using, right? It makes image processing tasks very feasible in real time. Um, Let me give you an example. If you're running an image, or if you're running an edge AI application on the drone, or you're running an edge AI application on your fixed position camera um, using like a Jetson, right? So these things, right, and an image processing ties on the edge is made feasible only with an image processing heavy image processing pipeline to run only on CUDA, right? So along with advantages, there are certain very obvious disadvantages, right? So very common disadvantages are it has a very limited function availability. At this point of time, there is only 250 functions which are available on the GPU version of OpenCV. Um, we have to handle the data transfer between the CPU and GPU memory as we were discussing, right? We have to we have to allocate a memory on the GPU, upload the files, and then download it back to the CPU. The other very obvious disadvantage is that since it's implemented using the Nvidia CUDA runtime API, therefore it is supported only on Nvidia GPUs, right? There is a very significant delay during CUDA startup, which makes the first operation, therefore the first operation takes a lot of time. There's explicit CUDA programming in C++ or C, right? So OpenCV provides access to image pixels to write custom functions. So you can write your own custom CUDA kernel, provided you have required knowledge of or you have pre-existing knowledge of CUDA programming. So what we have in mind for the future scope is that we would migrate the entire CUDA programming pipeline to C, C++, or C.
So let me point out the problem statement here. We have spoken about image segmentation, elevation classification, knowledge distillation. So what are we actually doing here? See, training aerial images, which are from drones and are of high resolution, are very difficult. Why? Because of the resolution itself, and in case there is a larger model that we are trying to train, let's say it consists of 1.4 million parameters, it becomes very difficult to squeeze everything in one GPU. And I'm talking about one GPU, which is probably of 12 gigabytes. Then when we need to have a larger GPU. However, the problem doesn't end there. We also need to have a smaller training time. See, because every AI ML use cases that we deliver, it probably takes from 2 to 3 months to develop and deliver to our customers. So we need not only a faster computational speed, we also need to deliver quality. And that is the reason we have been using multiple GPU or a distributed computing or distributed deep learning kind of a scenario. And we are trying to leverage multiple GPUs, either in one machine or in distributed machine. We are going to talk about both in our session today.
Hello everyone. Good morning and good evening. I'm Sushri Sulagnarath. I work as a cloud AI key expert at Siemens Advanta. My team and I are very excited to be a part of GTC 2022. So my colleague Indrajit had spoken about knowledge distillation in aerial image classifications, right? So what is a knowledge distillation? Let's get into that. So knowledge distillation is a procedure for model comparison in which a small model is trained to match a large pre-trained teacher model. Knowledge is transferred from the teacher model to the student by minimizing a loss function, which is aimed at matching softened teacher goals as well as the ground truth labels. So the training setting is also referred to as teacher-student training, where the large model is the teacher and the small model is the student. Knowledge distillation is often used to fine-tune the pruned model. The logics are softened by applying a temperature scaling function in the softmax, which is effectively smoothing out the probability distribution and revealing interclass relationship learned by the teacher. The knowledge distillation boosts the performance of a tiny neural network by distilling the knowledge in a neural network and mixing it up. So the basic idea of knowledge distillation is that the knowledge distillation consists of two neural networks, which is one is a teacher and one is a student model. The teacher model is a larger cumbersome model that can be ensemble of separately trained models or a single very large model trained with a very strong regularizers such as dropout. the cumbersome model or the teacher model is trained first. The student model, the smaller model, which will all use the distilled knowledge from the teacher network. It uses a different kind of training referred to as distillation to transfer the knowledge learned from the cumbersome model to a smaller student model. The student model is more suitable for deployment as it will be computationally inexpensive with the same or better accuracy than the teacher model. In our experiment, we have encoder-decoder based SegNet architecture defined for teacher and student models, whereas the student is comparatively a lighter version of the SegNet teacher model. We have followed the offline training for knowledge distillation approach where we first train the teacher model and then use it to train the student model with distillation laws. Over here we can see your teacher model, which is nothing but a SegNet encoder decoder network which consists of various layers of convolutional layers with batch normalizations and ReLU. During the training process, the teacher model is forward pass in evaluation mode, that is, the gradients are not calculated. The output of the teacher model is considered as soft levels for the training of the student model. The student model, which is shown over here, consists of also a SegNet architecture, which consists of convolutional layers with batch normalizations and ReLUs. But in comparison to the teacher model, the student model is much lighter in size because we have used smaller number of layers as compared to the teacher model. Due to the reduced number of convolutional layers, the student model becomes lighter and much smaller. Over here, we can see the teacher training and the student training process with a distillation. During the training of the student model, the KL divergence is calculated, which is a softmax function of teacher and student losses with respect to the temperature scaling function. This loss is called as the distillation loss. This distillation loss, in addition to the student loss, becomes the total loss on which the student model is back propagated on. So this loss is the main function or main loss function or upon which the student model aims to minimize on. Let's get to know that how the knowledge is distilled from the teacher to the student model. So knowledge is distilled from large complex teacher model to student model by using this distillation loss. Knowledge distillation uses generalization using soft targets that mitigates the cross overconfidence issue of neural networks and improves the model calibration. There are various advantages to the knowledge distillation concept. Like the knowledge distillation concept, upon using the knowledge distillation concept, it can be deployed at the edge. Knowledge distillation, a student model inherits better quality from the teacher and is more efficient for inference due to its compactness, needing less computational resources. It also improves generalization. The teacher produces soft targets for training the student model. Soft targets have high entropy, providing more information than one-hot encoded hard targets. Soft targets have less variance in the gradient between the training cases, allowing student networks to be trained on much less data than the teacher using a much higher learning rate.
So I'm sure by now you understand what is a knowledge distillation. And now let's try to build a classifier using knowledge distillation. So it's a multi-class classification. There are three classes over here. The first class is a desert, which has no greenery. The second class is a desert which has good amount of greenery. The third class is a desert which has sparse greeneries. What we are going to do is take a bunch of these videos, push them to a teacher and student model, and we'll try to see how it works. Now, here is the thing. We are trying to do distributed model parallelism in a single machine. That means the GPUs that you see here resides on the same machine. So how does it work? So treat this as one full model. If you treat this as one full model, what will happen is the teacher model will go ahead and run the forward pass. And as you can see, we will not take these hard labels. We will take the soft labels from here, and the student model will, which resides on another GPU in the same machine, will wait till the teacher model finishes the forward pass. And see, the reality is that we do train the teacher model for few epochs, like let's say 3 to 4 to 20 epochs max, so that it can extract good soft probabilities. We don't want a very noisy teacher. Okay, so once we extract those soft labels, we go ahead and pass it to the second GPU, and the second GPU does the KL divergence, minimization. Also, it does the categorical cross entropy minimization. So now you will ask me a question: why even do this? Because these GPU probably will be sitting idle. Well, not really. Understand this. These are huge amount of data that's coming in, and these are high resolution images. If I take them into frames, if I break the videos down into frames, they become images, and once those images are there, it's very difficult for the teacher model to even go ahead and fit the entire image or batch of images into one GPU, which let's say which will be of 8 GB. Now, what we are doing in order to utilize both these GPUs is batch by batch we are sending the images. So the teacher does the forward pass and does the minor training on batch one. The batch one goes, or the soft probability of the batch one goes to the second GPU, where the student model learns on the soft probabilities of the batch one. So how, you see how we are utilizing it? We are utilizing both the GPUs, and that's where we have gained a tremendous, I would say, use of computational power, or where we got benefited from using this mechanism of distributed computing by batch. Now let's bring your attention towards these set of images. Now they are not really images, they are actually video frames. If I talk about this one, is one video frame that we have explicitly taken out from bunch of videos. Now if you can see that there is a car over here, and the altitude is different on this image, on this image, on this image, this image, and this image. The further we go near the car, the much better we are able to understand that it is a car, and that's how the machine learning models also get trained. Now just think that if I go ahead and annotate this image, or let's say this image, and give only a bounding box across it, and then we go ahead and feed this type of resolution or this type of altitude to our machine learning model during the test time, and then we go ahead and give during the train time, and then we go ahead and give this kind of an image during the test time. What will happen is the model will not be able to go ahead and detect the car when it's the test time. The reason, because the model has never seen this data. It has only seen this data. It is trained on this data. So this is a scaling problem. Now we actually are trying to make our models altitude invariant. So in this situation, most of our images are taken on or taken at this elevation, and then what we are doing is we are going ahead and zooming into the image, drawing a bounding box, zooming into this image, and then drawing another bounding box. So in this way, we have various samples of the same image with different bounding boxes. Now we go ahead and feed this entire augmented data set into a machine learning model. So as you can see that we are taking the uh, images, and not only the single image, however, the augmented image and the associated bounding box, pushing it through a same knowledge distillation model. Now, I think Sushi has explained this model well enough that we extract the soft probabilities or the soft labels and then tell the student model to go ahead and predict on the soft labels, as well as there is another loss function which actually does the prediction of the hard labels. Okay, so this is a combination of two loss functions, this knowledge distillation, and it happens in a similar fashion where we send batches of images, and in this section there is something very interesting happens. This entire high resolution image is being patched. Just like transformers, we use the idea of patching. So as you can see that, and the entire thing is happening on one single machine. So these two GPUs that we have are running on one single machine, and the patches are being sent batch by batch with a positional encoding. Okay, however, it's not a transformer. It is not a transformer. It is a normal object detection which has also the bounding box coordinates. And what are we getting? I will tell you in the next slide as an output. After feeding these images and the bounding boxes to a machine learning model, what we are trying to achieve is a altitude invariant model. So what we are telling the machine learning model is, hey, go ahead and localize the object, which is a car in this case, in these various type of images. So we will, in this situation, let me just bring in the pointer. We can give the machine learning model either this the first image, the second image, the third image, the fourth image, or the fifth image. And still the machine learning model will say that this is a car. How? By minimizing a loss function that we have created. So now comes the interesting part. As you can see over here, it's a knowledge distillation, however, distributed into multiple machines and multiple GPUs. Now, quick note that these are not 4 GPUs. What we are doing is we are reutilizing 2 GPUs, both for student and teacher. So how are we achieving it? So let's say these are the video frames and these are the associated masks. Now this is an image segmentation problem. Hence we have to build this masks out of every frames and then feed the image and the associated mask to an encoder decoder network. So let's say that it's our encoder decoders which people have been using, like segnet, deep labs. So what we have done over here is we have divided the segnet, which is, let's say, a large segnet, into two blocks, block A and block B. The block A consists of encoder and the associated decoder. Block B consists of the encoder and associated decoder. And what we are doing is we are pushing these two shards into two GPUs. Okay, and we are extracting the soft distribution or the soft labels. And as you can see, this is output of those soft distribution. Now, you have to understand in real projects, it's not only just the forward pass. We do train the model for 20 to 30 epochs so that we don't have a noisy teacher. Okay, the teacher is good enough, and it also has learned. However, as I said, the goal is to shrink the teachers into a smaller student model. Hence, let's talk about how is it being achieved in a distributed environment. We have to have four workers. One worker is the master worker, which holds the soft distribution and in the parameter server. The master worker also goes ahead and tells the trainers, there are two trainers, which are rank 0, rank 1, the master is of rank 2, and the parameter server is of rank 3. So these are the four nodes that we're working on. And we see that the decoder that I spoke about, which is in the I would say the block A and block B are in a DDP wrapper, so wrapped around DDP. In other words, now what we will do at this point of time is to tell the trainers to go ahead and do the forward pass, because the trainer are responsible, the trainers are responsible for the forward pass when it comes to the teacher model. Okay, and then we go ahead and synchronize the so I would say weights, whichever weights we have extracted, and these are some of the weights, not entirely, and most of it is an activation. Okay, so these are what we call a soft probability, or sorry, a soft distribution. Now, once we get the soft distribution, it is there in the parameter server, and now we go ahead and use the same GPUs for training the student model. Now, the student model is, you have to understand, is a smaller version of the bigger model. Why we have a smaller version? Because we want to take that smaller model and store it, embed it into a TX2, a Raspberry Pi, which is available with us, and this TX2 will be used. It's a smaller one, which will be used on the drone or on a CCTV camera, to go ahead and get real-time inference. Okay, so that's the main goal, and that is the reason we're trying to shrink. Now, this works a little like architecture search. Why? Because we have also experimented using various of these student models where we have more than two trainers, and we tell the trainers, hey, go ahead and train or do the backward pass and the optimization on 4 or 8 in terms of even number GPUs. Let me explain a little bit on the student model. The student model also has two types of blocks, block A and block B, and includes the encoder and the associated decoder. And we are also telling that, hey, now the student model learn from the teacher model, and who will do it, who will enable that training are the trainer 1 and the trainer 2 nodes. Okay, and that's how we go ahead and get a mask out. And if you see, the mask gets classified really well. Okay, now think about this. When I put this put this model onto a drone, what we go ahead and get from the drone are these output images, okay, which can be used to send it back to the the station or the substation, where the image can further be processed and elevation information can be extracted and pushed to downstream applications. We need not go ahead and push the entire uh, image or the entire segment. We can highlight that these are the elevated parts. So as you said, highly elevated parts. So it depends on what do we want. Do we want the moderated elevations or do we want high elevations? If we want high elevations, we can configure the drone which is holding the TX2 and send only that information. It saves bandwidth. Okay, so coming back to the distributed mode, now the gradients are synced similar wise. Similarly, the gradient are synced using on the trainer 1 and trainer 2. Also, the uh, the the optimization or distributed optimization is done by distributed autograd. Okay, so that's the whole knowledge distillation. And remember, we are using the GPU. There are only two GPUs, and we are using it for the teacher, we are using it for the student. And as I said, even during the internal model parallelism, I would say that teacher, when it's getting the forward pass, we don't, the GPUs are not sitting idle, so we are removing that bubble. So that was the main idea of using distributed model parallelism uh, in, in a fashion where we go ahead and have, or we where we have no bubble altogether, as well as we achieve, or we're able to achieve the segmented mask faster. If you would have used a single GPU, this would have been never been possible.
Hello everyone, myself Vishal Pandey. I am a machine learning key expert here at Siemens Advanta. I'm very glad, very excited to be here. Uh, let's go on with the slides. So as Indrajit just mentioned you about the distributed computing part, let's go a little more deep dive into how it's actually implemented in PyTorch and in other frameworks in general. So now we'll start with the communication backends. So distributed learning requires workers to collaborate by swiftly sharing learned information with their colleagues. Now ML Benchmarks is a public and reproducible collection of reference implementations and benchmark suite for distributed machine learning algorithms, frameworks, and systems. ML Bench supports both one and multiple processes per node. In addition to multi-node training, communication between workers is crucial and will heavily affect performance. Now, currently, ML Bench supports three communication backends out of the box. Those are MPI or message passing interface, Glue available with PyTorch, along with Nickel, high-speed connectivity between GPUs if used with correct hardware. So each backend represents its benefits and advantages, and is designed for specific use cases, and those will be reflected in the results. So as we can see, MPI, glue, nickel, all are out of the box, just broadcast, just have features like broadcast, all reduce and all gather on GPU, as well as and a glue is for the same thing on CPU. So, and however, there is a one difference here, that is MPI does not support float 16 as of now. And yeah, so this is important to note that PyTorch that is built from source comes with nickel and glue pre-installed. So yeah, fast multi-GPU collectives with nickel. Now today, many servers contain 8 or more GPUs, but in practice, the benefit of scaling an application using multi-GPU can be difficult to obtain due to the following reasons: that are enough parallelism that has not been exposed to efficiently saturate the processors. Processors exchange too much data and spend more time communicating than computing. Now, to avoid such bottlenecks, it is important to make the most of the available inter-GPU bandwidth, and this is what Nickel is all about. NCCL, produced as Nickel, is a library of multi-GPU collective communication primitives that are topology aware and can be easily integrated into the application. Nickel is designed to be lightweight, depending only on the usual C++ and CUDA libraries. Nickel can also be deployed in single process or multiprocessor applications, handling required inter-process communications transparently. Now, the collective communication routines are common patterns of data transfer among many processors. So, when we have multiple GPUs, it's imperative to transport data from each of them, right, into one another and amongst themselves. Now, all the collectives can be performed either out of space or in place. All reduce starts with independent arrays Vk of n values on each of k processors and ends with identical arrays s of n values. Now where sk is equal to v naught k plus v1 k plus vk k for each processor k. In all gather, each of k processors begins with an independent array of n values and collects data from all the other processors to form a result of dimension n by k. Similarly, in broadcast, an element buffered on one processor is copied to all other processors. So as we can see here, in the first picture, we have a GPU 0, GPU 1, GPU 2, GPU 3, and all these all reduce what does is it combines all of the information from all the four GPUs, and it presents a copy of that snapshot on all other GPUs. In the next in all gather collection, you can see that GPU 0, GPU 1, 2, and 3, these all contain different information elements that are termed here as A, B, C, D, and all these are grouped together. Now in broadcast, as shown here, we have only information only on one GPU, that is GPU 0, and that's termed as A, which is now broadcasted to all other GPUs, remaining GPUs. So GPU 1, GPU 2, GPU 3 now all have this specific information point A mentioned here in copied to all other GPUs. So that's the broadcast. Moving on to the PCLE technology and the two-step tree algorithm. Now, to implement collectives efficiently, the topology of interactions between processors will be taken into account. Consider a broadcast of data from GPU 0 to all other GPUs in the PCLE tree topology. As mentioned in the picture here, a two-step tree algorithm is a common choice here, because we send data from GPU 0 to GPU 1 in the first step, and then GPU 0 to GPU 2 and GPU 1 to GPU 3 in the second step. Now we can perform the initial copy from GPU 0 to GPU 2 and then GPU 0 to GPU 1 and GPU 2 to GPU 3 in the second step. Now when examining this topology, it is clear here that the second option is preferred, since sending data simultaneously from GPU 0 to GPU 2 and GPU 1 to GPU 3 would cause contention on the upper PACLE links, having the effective bandwidth for this step. To optimize this broadcast bandwidth, the better approach is to treat the PCLE topology above as a ring. The broadcast is then performed by relaying small chunks of the input around the ring from GPU 0 to GPU 3. So as we can see here, ring algorithms provide near optimal bandwidth for nearly all of the standard collective informations operations, even when applied to tree-like PCLE technologies. So now, GPU collectives with nickel, how does this come to the picture? So in order to provide maximum bandwidth, nickel implements ring style collectives as just shown in the previous slide here. In order to minimize memory overhead to a few megabytes on each GPU, Nickel splits large collectives into many small chunks. It would be highly inefficient to launch separate kernels and CUDA CPY calls for every step and chunk of a collective algorithm. Instead, each collective is implemented by a monolithic CUDA kernel. Nickel makes extensive use of GPU direct peer-to-peer direct access to push data between processors. Where peer-to-peer direct access is not available, the push data is staged through a buffer in pinned system memory. Similarly, synchronization is performed by polling on volatile variables in device memory. Now, internally, Nickel implements each collective in terms of three primitives, that is copy, reduce, and reduce and copy. Each of these is optimized to effectively transfer fine-grained slices of data between GPUs. The kernels have also been specifically optimized to achieve maximum bandwidth at low occupancy. As a result, Nickel can saturate a PCIe 3.0 into 16 interconnect using a single block of CUDA threads. This leaves the bulk of the GPU free to execute compute tasks concurrently with the communication. Nickel currently supports the all gather, all reduce, broadcast, reduce, and reduce scatter collectives. Any number of GPUs can be used if they reside in a single node here. So that's the you can say the benefit of the Nickel here. So Tosh.distributed supports three built-in backends, each with different capabilities, all the Glue, MPI, and Nickel, as shown in the table below. Moving on to the Nvidia Jetson TX2. Now, what we have done and we have planned is to implement this technology after training during the inference. We would be needing Jetson TX2. So all the inference part of the student model now happens in the TX2 itself. Now, what is Jetson TX2? So Jetson TX2 is an embedded system on module with dual core NVIDIA Denver 2 plus quad core ARM Cortex A57, 8 GB 128-bit LPDDR4 and integrated 256 core Pascal GPU. So it's a very powerful, you can say, mini supercomputer type hardware available here. It's useful for deploying computer vision and deep learning modules. Jetson TX2 runs Linux and provides greater than 1 teraflops of FP16 compute performance in less than 7.5 watts of power. So that's all. I'll be handing over to Indrajit now for quick questions and wrapping up the session. Thank you all. It was a pleasure being here.